Hi, my name is Sukhmani Sethi. This is my lab report for Physics Lab 1. The purpose of this lab is to visualize motion with a constant acceleration and compute data to create a predicted model with and without drag and compare it to the actual data derived from the experiment. The models used in this lab include the predicted models with and without drag made with FlowScript and the experimental models created from the data from the tracker software in Google Sheets. The calculations of this law rely heavily on Newton's second law, which states that force is equal to the acceleration of an object times the mass of an object. It shows that if there is a constant acceleration, the force is constant as well. Drag force opposes an object's motion through a fluid-like air and increases as the object moves faster. The drag force is given by this formula. This force acts in the opposite direction to the object's velocity, reducing its speed over time. The video consisted of me dropping a crumpled up paper ball next to a meter stick.
Wait, hold on. You set it off.
Observations from the video include there was acceleration due to gravity.
Wait, hold on.
The x and y-axis were tilted by 90 degrees because the video was inverted sideways, and the origin was set to when the ball came to rest. The x and y-axis were tilted by 90 degrees because the video was inverted sideways, and the origin was set to when the ball came to rest. The tracker software was used to plot the position points of the paper ball to collect data and created the following graph. The data was cleaned just to have the points in which the ball was in motion. Then a FlowScript code was created to predict the motion of the ball with and without drag. For without drag, the code was modified for the correct time intervals and the acceleration was set to 9.8 as a constant acceleration. To make the code account for drag, I added a drag force that slows the object down as it falls. This drag force depends on how fast the object is moving. It increases as the object speeds up. I combined this drag force with gravity to get the total force acting on the object. The total force was then used to update this object's speed and position. As the object falls, the drag force grows stronger and eventually balances out the pull of gravity, causing the object to stop speeding up and reach a terminal velocity. These are the graphs created by the code. This was the final graph created, and it compared the actual model to the predicted models. The actual model was more similar to the predicted force with drag, indicating that there was a drag force in the motion. The velocity versus time graphs show that without drags, the velocity keeps increasing, while with drag, the velocity will level off, which indicates terminal velocity. Only the model with drag predicts a terminal velocity, and this happens because the drag force eventually balances out the gravity force, which stops further acceleration. When terminal velocity is reached, the net force becomes zero because the upward drag force equals the downward gravitational force. This means that the object moves at a constant speed without accelerating. If the object was thrown downward, the terminal velocity would be the same because it depends on the balance of the forces and not the initial velocity, but the object will reach terminal velocity faster if thrown downward, but the final speed will remain the same. Models assume ideal conditions that don't reflect real-world conditions, which leads to differences between the observed and predicted data. The drag was not accurate because the air density and the area of the paper were not accounted for.